like I said in this section, solve trig equations again, but you're not going to be able to solve them initially in the format that they are. You're going to have to do something to adjust the equation. And that tends to sometimes be a hard thing for people to do or to recognize why they have to do it. My biggest suggestion to you is that when you're solving equations, a lot of times maybe one of the things that you want to use, or the things that we use currently, is factoring. And when we want to factor, thinking about like factoring any quadratic equation, isn't it a lot easier if it's all x's instead of x's and y's? Go back to algebra 2, maybe you factor some things that look like x squared plus 2xy plus y squared. Those were kind of hard to factor. If we can avoid those types of things, we're going to try to do that. So when I look at this first equation here, that's the issue that we have going on here. We have a sine, and it's to the first power. And we have a cosine, and that's squared. Okay. So if I was using kind of an algebraic process here to say, let's let if you let u equal sine of theta, can this be written as u squared then? No, u squared would be sine squared of theta, wouldn't it? Can you make the substitution then? No. So you'd have to maybe say u squared is equal to, or sorry, not u squared, maybe you bring in another variable, say v squared is equal to cosine squared. And now algebraically, don't write this down because you're not going to do it this way. You'd have something like that. And if I wanted to factor that, I'd go 2v squared minus u minus 1. Well, that's going to be really hard to factor because they're not like terms, right? They're not like variable components. So we struggle with that. So when you see inside your equation two trig ratios that are not the same, two trig functions that are not the same, so in this case sine and cosine, you want to see if you can make a substitution to rewrite one of them, okay, in terms of the other one. And usually the ones that you can do that with are the ones that are squared. Okay, so when I look at this cosine squared one, that's the one that I'm going to kind of replace because I can write that in terms of sine. Because don't we have this thing here, cosine squared theta plus sine squared theta is equal to 1? Does that mean that cosine squared theta is equal to 1 minus sine squared theta? Is that okay? So now do you see how you can replace that thing right there with that? And now we'll end up with 1 plus sine theta is equal to 2 times 1 minus sine squared theta. And now the issue of having a sine and a cosine has disappeared. Okay, and that's one of the benefits. It's one of the main purposes of why we spent so much time in 7.1, 7.2, and 7.3 learning all those identities. Because when we get to equations, we might have to alter the initial equation so that we can address it algebraically. Okay, if we're going to address this graphically, we just type both those sides in to our calculator and see where they intersect. If I want to find those intersection points algebraically by hand, I have to know my identities to make these substitutions. So we can put it into a form that we can deal with. So this is going to be 1 plus sine theta. I'll distribute my 2. So it becomes 2 minus 2 sine squared theta. Now I have sine squared, so when I see that, I'm probably going to think factor, so I'm going to get things equal to 0. So I'm just going to move everything over to one side. So I'll add 2 sine squared to both sides. I'll subtract 2 from both sides. And I should get that. And at that stage, you now have a 7.4 equation, okay, or an equation similar to that of section 7.4. In those that we did in 7.4 of this form, because this is quadratic, okay, we have something squared, something to the first power, and then our constant. Okay, so we got like an ax squared plus bx plus c format here. I think a lot of us are starting to see that maybe we like this. Let u equal sine theta. So u squared now, you can substitute as sine squared theta. So now we can go through and say, okay, 2u squared plus u minus 1 is equal to 0, correct? I'll go ahead and factor that. Now to factor that, we have to use the A times C method, right? Or you can use the quadratic formula. Maybe let's do the quadratic formula. Just because we haven't seen maybe too many examples this way. Remember when you do the quadratic formula, it's always solving for your variable. So right now our variable is u. So we'll say opposite of b, so negative 1, plus or minus b squared minus 4a times c all over 2a. Okay. So now I get negative 1 plus or minus. All right, so this thing's negative 4 times negative 1 times 2 is 8, right? So we get 1 plus 8, which ends up being 9. Let's square root of 9. 3 all over 4. When this becomes a perfect square, this is not something we talked a lot about when we, no textbook is going to write this, but if that thing becomes a perfect square, ultimately that tells you that the factoring of this thing could have been done using one of your shortcut techniques, like maybe the AC method or the product of sum techniques and stuff like that. But if I look at this, this becomes negative 1 plus 3, so that's 2 over 4. Or negative 1 minus 3 is negative 4. Negative 4 divided by 4 is negative 1. Okay? So there's my solutions for u. U is equal to a half or negative 1. But what was u? Sine theta. So sine theta is 1/2. Or sine theta is equal to negative 1. All right? So we've solved for sine theta, but remember the overall goal here is to solve for what? Theta. Okay, so think about your unit circle, because this number here is a really nice number that should exist on the unit circle, so we don't need to use our inverse ideas on our calculator. We're using the inverse idea with our unit circle picture. What angle will give you a y value of 1/2 on the unit circle? Pi or 6. Okay, that's in the first quadrant. Where else is the sign positive? Second quadrant, right? So what angle is a reflection of pi over 6 in the second quadrant? 5 pi over 6. Okay? So again, all we're doing there, guys, looking at our unit circle, we know that we've got these ordered pairs for these angles, right? This ordered pair right here is radical 3 over 2, comma 1/2. That right there is the sign, right? So we're saying, okay, what is the angle that shows this y coordinate being 1/2, and we know at that angle, which is that one right there, is pi over 6. Then we mimic that over here, because that y value is also 1/2 there. So we figure out what that angle measurement is, and that angle measurement is that one. It goes from the positive x-axis all the way up to that terminal ray, and that's 5 pi over 6. Okay. When is sine equal to negative 1? When is the y value on your unit circle? So look at that thing right there. Where is my y value, negative 1? Right there at 3 pi over 2. So theta is equal to 3 pi over 2 here. Okay. I think some of us are seeing this maybe in the homework. If they do not tell you a specific unit, then they imply radians. And in WebAssign, a lot of times it's something we overlook. They'll have that little box, and then on the right-hand side of that, they'll have their units already typed in, and it'll just say RAD. So make sure you're putting radians in. Or they will say, write your solution kind of like this. they'll say, solve the equation 1 plus sine theta equals 2 cosine squared theta, and then we'll write on the interval, and they usually put a bracket, 0 to pi, and then a parenthesis, and all that means is make sure that you're doing it in radians, because 2 pi is in radians, right? And right there, all it means is that you have to do is write your first set of initial points. You don't need the infinite points, okay? Now, why do anybody have any ideas on why they put a parenthesis around 2 pi but a bracket around 0? It's the same point, okay? It's going to be the same thing because 0 and 2 pi, or 0 and 360 degrees, are coterminal positions, right? So the reason they exclude one of those is so that you don't have redundancy in your solutions, okay? Not a huge deal, but it is something to think about and realize why they're doing it. If they want the infinite solutions, they will verbalize somehow, kind of like find all solutions of the equation or something like that. So if I wanted all solutions right here, what would I have to do to these two values here? What do I need to add to pi over 6 so I get infinite solutions? 2 pi, okay? What would I have to add to this one? 2 pi k, okay? So when I write it this way, and you might see it, I don't know, from textbook to textbook, author to author. Sometimes, like if you do a Google search or something like that, you might see something like this. You might see like that means so that curly brace means that we're going to start putting solutions in, and then they might say, well, your solutions are pi over 6, 5 pi over 6, and they put as many as you have in here, and they put that in parentheses, and then we'll put 2 pi k. Okay, then they'll write sometimes a bar here, put k, tell you that comes from the integers, and then they'll put that final curly brace on. And all that means, guys, is this number here plus the 2 pi k is a series of solutions, and then that number there plus 2 pi k is another series of solutions. Okay? It's a more concise way of writing things. And if you've never seen that before in class or explained to you, I think sometimes reading something like that might confuse some people and where it comes from, what it means. And that, I think, just from my own experiences, going on to other math classes, a lot of times notation isn't described. They just start using it. And for some reason, then a lot of times the author, maybe even the professor, expects that you've seen it or that you understand it, or you can take the time to figure out what it means on your own, which I think is one of the harder things about math. So I want to show you those things. We can graph these. Obviously, this thing here is going to be just a sine function shifted 1 unit up. So sine of x plus 1. And the other one was, what was it, cosine squared? If we look at those, make sure that's what I had. 2 cosine squared. So then we see that the places that we're looking for solutions are the intersections of the green curve and the red curve. I'm not sure why it won't give me all of those when I click on these this way. So if I look at those, okay, 2.62, that's 5 pi divided by 6 as a decimal. 0.52 is pi over 6 as a decimal. And 4.71 is 3 pi over 2 as a decimal. Okay. And you see then that those are between, if we look at like x equals 0 and x equals 2 pi, you see that those are between those two blue vertical lines. So that means that those are the only 3 solutions in the interval 0 to 2 pi. Okay. Do those get mimicked then if I look at 2 pi to 4 pi. Does b, if I take the x value of b and add to it 2 pi, but keep it on the same y value, keep it on the same horizontal line, so that horizontal line is 1.5, does that provide that point D? So you see that B and D are replicated, okay? So this one here, this point is generated by taking pi over 6 plus 2 pi k. In this case, k is 1. This one here would be 5 pi over 6 plus 2 pi k, where k is 1. And this one would be the 3 pi over 2 1. Does that make sense, everybody? And then we can keep going. So this point here, all it is that k goes to 2 now. And this point here, k goes to 2. And that's going to find you those infinite points as far out as you want to go. Does that make sense? Okay. All right, so that being said, let's take a look at one other. And I want to show, I want to go back to a little bit of algebra before we kind of start on this one. You guys remember doing something like, let's just start with the square root of like x plus 3 and see if that ever intersects, let's say, I might have to adjust that a little bit. Let's go just the square root of x plus 1 . Okay, so we did some equations early on that kind of look like this. And actually, let me do one more thing real quick. And I still don't know 100% if this is going to kind of prove my point. Plus 2. All right, so maybe something like that. And we're looking for, ultimately what happens is our solution ends up being 1, where these two things cross, right? Okay. But if you remember what we really did algebraically, in order to solve both of these, we would isolate one side first. So getting one radical isolated all by itself, and then we ended up squaring both sides. Okay, so what happens then is if I take f of x and I square it, it looks like that. And if I find g of x and I square it, it kind of looks like that. And what we go through is say, okay, now the solution of this one is what we would find by hand. It makes it a little bit easier if we were to actually do the algebra here. I don't know if, no, it's the way it's actually got it set up, and won't do the algebra. But that would eventually get rid of the square roots. Does that make sense? Okay. Do you see it? The solution to the orange one and the blue one, the x value is still the solution to this one over here. Does that make sense? Okay. We also found out maybe if I took like maybe if this one was just like x, so it's the line y equals x. Okay. You see there, and let's make this one -1. Not what I want. Okay, so this one, you see that if I had like the equation square root of x equals x, this is the picture we're looking for, and there should be two solutions, right? Okay. When we square both sides, we get these two pictures, again having two solutions. Do you remember ever coming up with an equation where we squared both sides, and the green plane there, the green XY axis, actually produced more intersections than what the original equation had? You guys remember doing that? Okay. And those extra solutions didn't necessarily become solutions for original equation. Those extra solutions, what do we call extra solutions that develop through our algebra? Extraneous. And they develop every single time that we end up taking an equation, squaring both sides, they have the potential for showing up. Okay? So, in this type of situation, I was trying to write an algebraic equation up there. For some reason, I can't generate one the way I want to. But we always have to go back. When you square something algebraically, go back and make sure all your solutions are true or they all work. So we're going to kind of come back to this picture when we're done with our specific equation. Now, they're only asking us to do this between 0 and 2 pi. Okay? So we want to be in radians. That's one thing that tells us. The other thing it tells us is that we don't have to do the 2 pi k thing. Okay? We can be done once we find our initial solutions. But what is the issue here? Just like the last question, we've got varying trig functions, right? Now, the last one we were able to substitute because of the sine squared or cosine squared situation, correct? Now we can't substitute because they're all to the first power, okay? But we can kind of quickly address that because we can do anything to equation that we want to, right? So there's nothing stopping us from being able to do that. Square both sides. Squaring the right-hand side is pretty easy, sine squared. And the left-hand side, you have to FOIL that out. So quick cosine times cosine will give me cosine squared. I'll multiply these two things together and double it. So it gives me my middle term, 2 cosine theta. And then I square my last term. Now, does that equation look somewhat similar to the last question we did? Okay. Still now have an issue because there's cosines over here and there's sines over here. We need to replace one of them, and it only makes sense to replace a specific one. You can't just replace any one that you want to. Which one makes most sense here to replace? Sine squared. Because if I replace this with like 1 minus sine squared, which is legal, you would have 1 minus sine squared over here, plus 2 cosine, plus 1 equals sine squared. You'd still have sines and cosines, right? If I replace sine squared with what it is equal to from the Pythagorean identity, we get this thing here, right? So now that's nice because you have now dwindled this down to a 7.4 equation. Okay, through the use of one substitution. And I guess one algebraic process and one substitution. Now you should solve for cosine squared, or sorry, cosine, by adding cosine squared to both sides and subtracting 1 from both sides. And when I do that, we get something that looks like that. Do you guys agree with that? Ones cancel each other out. Add cosine squared give me 2 cosine squared. What do these two terms both have in common? 2 cosine theta. So when I take out 2 cosine theta, it leaves me cosine theta plus 1 equals 0, right? So this then is 2 cosine theta equals 0. And this gives me cosine theta plus 1 equals 0. So this is going to give me cosine theta equals 0 when I divide both sides by 2. And this will give me cosine theta is equal to negative 1. I'm going to take this stuff, start writing over here. When does cosine, if cosine theta is equal to 0, What value of theta gives me cosine to be 0? On my unit circle, where is the x value 0? Pi over 2 and 3 pi over 2, right? So there's two solutions for that one. Now I also have the solution for cosine theta is equal to -1. So where is theta? If theta, or what angle of theta gives me the x value on my unit circle to be -1? Pi. Okay. Now, because we squared things, this is always something you got to pay attention to. Because we squared things, these are only possible or potential solutions. We got to go back through and check. Okay? So in the event of checking, we would just plug those solutions back in here and see if we get true statements. I'll finish this during my planning period, showing you the check, but we'll pick up with it again tomorrow and make sure that we all see that. All right, so checking these solutions. It's pretty easy, actually, to check these. I'm just going to go cosine, plug in these solutions. So pi over 2 plus 1. We're going to see if that gives me sine of pi over 2. Cosine of pi over 2 is 0 plus 1. Sine of pi over 2 is 1. And we ask ourselves, is that a true statement? Yes, it is. So pi over 2 is a solution. Pi over 2 works. Then we go to the next one, which is 3 pi over 2. So we have cosine 3 pi over 2 plus 1 equals sine of 3 pi over 2. Cosine of 3 pi over 2, again, is 0 plus 1. Sine of 3 pi over 2 is -1. 1 does not equal -1. Not true. So this is not a solution. It's an extraneous solution. Extraneous, maybe root, if you want to think about that, or 0. Now I got to try pi. So put cosine of pi in, plus 1. Does that equal sine of pi? Cosine of pi is -1. Sine of pi is 0. So -1 plus 1, does that equal 0? Yes, it does. So pi is our other answer. Looking at that graphically then, it should make sense. Look at this one here. I think we had cosine of x plus 1 and sine of x. Just double check. Yeah, cosine x plus 1, sine x. So we're looking in the interval from 0 to 2 pi. So you won't have to normally do this, but let's just say we're just going to focus on that interval. Let's take this. Also focus on that interval, just so nothing else graphically shows up. And we get that there. Okay, that series occurs. If I ask for the intersection points, one of them is 3.14, so there's the pi, and the other one is 1.57, which is your pi over 2. So those were the two solutions we came up with. Now, why do we get 3 algebraically? Because when we square things, okay, so if I take this left-hand side of our equation, we squared that. So it's going to look like f of x squared would look, between 0 and 2 pi, would look something like that. And then if I take the g of x, which is sine x, and I square that, it's going to look something like that. Now, how many times do these things intersect? These things intersect at that point. And that point, or those other 2 points. And we see then that because we squared something, we get 3 solutions. But inside those 3 solutions exist the solutions to my original equation. Okay? We just have to decipher that one there, point E, or sorry, not point E, point D, is ultimately not a solution. That's 3 pi over 2. 3 pi over 2, though it's a solution for when I square things, it was not a solution for my initial one. So we got to kick that one out. But yeah, so because they asked me just between 0 and 2 pi, I don't need to look at these things repeating. If they didn't provide that restriction, then obviously, won't let me do it. Obviously, then we would just take our solutions and add 2 pi k to that one, add 2 pi k to that one. If this said something to the effect of infinite solutions or all solutions or something like that. Okay. So yeah, that's kind of the check on those. And that's the thing. You always need to check when squaring an equation. When you square both sides, you need to check for extraneous solutions because that algebra could potentially generate them. And the reason they could happen is that idea of that we're transforming the graphs. Okay, and they could end up having additional intersection points that don't exist inside the first equation.